So in this lecture, we shall learn how we can model, analyze and design a composite platform, that is a platform made of steel structure with a composite deck on top, and how we can assign the seismic definitions as per the International Building Code, that is IBC 2010. And after that, we shall learn how we can do the direct analysis of the steel structure with the notional load requirements as per the AISC 360. And in the end, we shall learn how we can assign the design commands and design the structures as per the AISC 360, that is American Institute of Steel Construction Code, and with the help of allowable stress design concept, that is ASD concept. So my objective of this lecture is that you should be comfortable in the steel structure. Second, you should be comfortable with the American code design, and third, you should know how to do the direct analysis of the steel structure. So first of all, we model the composite platform. Name the file here, enter the space and enter the units as meter and kilonewton. So after that, we can open the stat editor file here. So units can be meter and kilonewton. After that, joint coordinates 1, 0, 0 and 0. So we can press Shift plus K option on a keyboard, and after that we can press Ctrl C, Ctrl V option on our keyboard and select the access 7.25 here. Similarly, again copy this particular node to 7.25 here, and translationally repeat this whole structure along Z axis with the default step spacing of 5.25 meter and number of steps as 3. We can select link steps option here. So after that, we do need to translationally repeat these joint SAT along global direction Y, and default step spacing we can select it as 3.5 meter, and we can enter the option of link steps here. So after that, we can model this platform here. Although you could have saved this effort just by modeling this particular portal and translationally repeating this, but just to make the things clear to you, I am following this conventional approach, because in the beginning I don't want to increase the speed of the lecture here. So this is just a simple platform that we are talking about, and after that we can delete these beams here. So this is just a simple platform that we have modeled here. After that, we do need to model the slabs for the composite deck. So before we start the modeling and I make you familiar with the unfamiliar or uncommon terms here, so let me explain the simple concepts of this composite deck system. So you can refer to the steelconstruction.info website. So here there's an option called floor system here. So on the right, you will see this deck system that is being followed here. So what drives the choice of this floor system? Basically, this is a very economical, and in those countries where the shuttering cost is very high, it can help us in reducing the shuttering cost also, and basically it helps in reducing the cost of the structure also. And speed is also very good if we are following this approach. And service integration is also very good here. That is, you can see this is the composite deck, and below that these pipes are just hanged from the top here. So here also you can see that this is the composite, this is the deck sheet here, and from the deck sheet you can just simply hang the services. And adaptable space also, aesthetics, acoustics, fire resistance, thermal mass. You can read this if you are unfamiliar to this approach. but this is the main diagram that like main thing that can make the things clear to you. That is how we can how this deck system is laid. And after this, the reinforcement is also like laid on the top face, and accordingly the concreting is also done. So this is just a small video here that they have shown here.
Composite floor slabs generally
So here you can see that this is basically the system on which these deck sheets will be laid down. And there's one thing that I want you to notice, that this is the shorter span and this is the longer span. And when we are putting this deck sheet here, the grooves will be laid along the shorter span only. This is the mistake that most of the new people do. They simply don't understand what should be the orientation of these deck sheets. So this is the golden rule, that the grooves shall always be these grooves shall always be parallel to the shorter span, not parallel to the longer span. Because otherwise, as I always also explained you the system of the one-way slab and two-way slab in the previous lecture. So the deck sheets are almost of the time laid on this one-way system only. So after installing these deck sheets here, we do we cast the stud anchors here. So here you can see that basically studs are now welded so that there is a proper interlocking connection between this steel deck plate here and the structural steel member here. So now we have integrated the steel structure with the deck system here. Similarly, these stud bolts are also casted here, and after that basically they put the reinforcement cage or wire mesh here, and after that they put the concreting here. So after that it just becomes a typical floor here. So this was just a small video here. So this is just a simple video here. Here we can see that this is basically the steel deck here, and on the top the reinforcement is already laid, and on the top of that they are pouring the concrete, so that there is a particular this RCC floor system here on the top. So these videos were just to explain you the basics, that what exactly is the concept of the steel deck system here. And accordingly you can Google the images also if the things are not clear to you. That is, here we can see that this is just a typical cut section here. That is, this is the steel deck, and on the top of that there is a concrete slab here. This is also a good cut section. This is basically the stud anchor here. These stud anchors are basically mostly in the diameter of this 19 mm. The minimum diameter of this stud bolt is 19 mm, and this stud concept is widely used in the bridges also. So if you are a bridge designer, you should know that when we are making the RCC slab on the top of a steel girder, so to integrate that we do place the stud bolts here. So coming back to our topic here. So basically when now we want to place the steel deck floor here. So for that basically we first of all need to model the one-way slabs here. So this span is approximately 5.25 here, and this span is approximately 7.25 here. So we can insert nodes. Let us say we insert 3 nodes here. So left click on OK here, and we can left click on geometry, add beam by perpendicular intersection. So now these slabs are one-way slabs here. That is, this span is only 1.8125 and this span is 5.25. So this particular slab will be a one-way slab here, and same shall be the case for all the further for all the further slabs. So similarly we can model the beams here also. Similarly insert nodes here also. N equal to 3, geometry, add beam by perpendicular intersection. So now we have basically made a basic model of the this steel composite deck system here. So in the next lecture we shall start with the further options, that is how we can assign the releases, how we can model the composite deck, etc. So in the previous lecture we have learned how we can do the basic modeling of a composite deck platform. In this lecture we shall learn how to model the composite deck. So in the previous lecture also I had did the basic explanation of how we can model the composite deck, but in this lecture you shall learn the practical aspect of doing that. So for that first of all we need to go to geometry, and then we need to go to this composite decks option here. So here there are various options, that is it is asking that whether we want to create a new deck. So left click on this option here, and then we can just simply draw a composite deck here. So we can name it as composite deck as D1. So left click on OK here, and here we can see that the direction is very important. So right now it is 14.5 by 15.75. So we need to left click on D1 option here, and then we need to enter this data here, that is we need to enter the concrete thickness, we need to enter the unit weight, your concrete grade, etc. So concrete thickness above fluids and this rib width and rib height. So before we enter this data you do need to understand the basic aspects of all of this. So first of all, let us say I have opened this typical deck sheeting of an Indian vendor. So here we can see that first of all he has provided this trapezoidal decking profile, and here the rib width is 25 mm and the rib height is 44 mm. And if we go to the higher capacity deck sheets, here we can see that the rib width is approximately in the range of this 250 mm and the rib height is in the range of 52 mm. And all of this data for all the deck sheet, the vendor do provides the typical allowable loads for a particular span. So here also you can see another decking profile here. So the rib width is in the range of 118 mm and the rib height is 75 mm. So these are typical fixing arrangement details, that is at the end we do need to provide this end closure angle details. And here also you can see that these are the studs that we do need to install to fix the these deck sheets, and this is basically the arrangement with which we overlap the deck sheets. So this is also a very widely asked question, that how we can overlap the deck sheets. So this is the typical arrangement. And before coming back to our lecture, I want to explain one more concept to you, that is this option here, that is showed and unshowed option. So basically here you can see that this is the basic image of how we make the deck sheet arrangement. Here you can see that there are no supports to the deck sheets here. So the system in which we do the concreting of the deck sheet without having any support in the bottom is called the unshowed construction. And showed construction is the one in which the deck sheet does not have like much capacity to carry the wet concrete load. So what we do need to do in that case is that we do need to provide the shuttering on the bottom. So in that case it is called the showed construction. So in unshowed construction you need much higher capacity of the deck sheet as well as for the structural steel, whereas for the showed construction the capacity requirements are lesser. So that is why the stat asks us whether we want to go ahead with showed or unshowed construction. So entering the data here, concrete thickness above fluid, let us say we enter it as 99 mm. Unit weight concrete we can enter as 25. Grade we can enter 25,000 kN per meter square. After that it is asking that whether we want to use any particular database here. So instead of using the by default database, we can enter the rib width as 0.105 and rib height as 0.046 mm. So stud diameter we can enter it as 19 mm. So this is the minimum diameter of the stud that is available in the Indian as well as in the international market, and stud length we can enter it as 120 mm. So taking the construction as unshowed only, so left click on update deck property. So we do need to left click on this update deck property, otherwise all these properties shall not be saved. So here we can see that this now property is now saved. So here also you can see that it has, when we left click here, all the beams are like having an effective span and the properties. So the method with which we do need to work in the start is that first of all we need to be clear of all the setup option here. After that we need to be clear of all the geometry options here. So we have entered the composite deck as required and we have entered the beams also as required. After that we need to go to general here. So in the general we have all the options that need to be satisfied before we go to the analysis command. So keeping things short, what exactly we do need to do now is that first of all like we do the easiest part, that is we enter the supports here. So to make the things somewhat complicated, we go ahead with pinned option here, cause in the case of pinned structure all the moments shall be balanced on the top itself. So basically in that case we do need to provide a bracing here also, cause there is no as such capacity of the of the structure to handle the lateral forces. So we do need to provide a bracing here. So we can provide a simple cross bracing here. So now we are done with the supports option also. After that we do need to enter the properties here. So properties of the structural steel sections can be entered in the form of various ways. So most of the people are much familiar with the RCC part of the software, but they are not much familiar with the structural steel part. So in structural steel we can have we can enter properties with the help of various options. That is, we have section database option also, and we have define option also. So to make the problem much more complex and to have your exposure to all the options, what I will do is that I will enter the properties with the help of section database also, and then enter the properties with the help of define option also. So left click on define option here. Here we have an option of tapered eye. So this tapered eye option is very important, and in the further lectures when we will study about the PB sheds, so there you will see that this tapered eye option will will be of very much useful to us. So in this tapered eye option we can enter depth of section at start node, let us say 0.516, and thickness of web we can enter it as 0.008, depth of section at end node, that is 0.516. So in the case of PB shed, what we do is that we increase it to, let us say, 0.716 also, to make the profile as per the bending moments. And width of top flange we can enter it as 0.25. with thickness of top flange we can enter it to 0.016. same for the bottom flange also. Left click on add here. So for the main beams that are having the maximum like bending moments, we assign them this taper section. And after that, when we go to this when we want to enter the properties for the end members here, we can enter depth of section at start node as, let us say, 0.416, thickness of web 0.008, depth of section at start node 0.416, width of top flange we can enter it as this 0.25, 0.016, 0.25, 0.016. Left click on add here. So for the end section we can assign the properties here also. So these are the like built up section properties that we have assigned here, and when we check that in the 3D view, these are the simple I sections that have been modeled here. After that, to make the things somewhat more interesting, what we can do, we can left click on section database here, and we can go to European section, and we can select IPE, that is I sections only. Let us say we choose IPE 240 here. So left click on add here, and all these sections that are supporting the deck sheets here, we can assign it as IPE 240. And let us say if we want to assign the W shape sections as per the American standards, so we can left click on section database here. We can select American and W shape, and we can select, let us say, W16 into 45. So left click on select here, and left click again on add here. So we can go to select beams parallel to y-axis, and we can assign this W16 into 45. Now the next step should be the orientation. What exactly is the orientation of this column here? So when we check the 3D view here you will see that the orientation of the column is like this. So this shall be the moment resisting frame here. For those who are not familiar with the concept of moment resisting frame and shear resisting frame, I shall explain you in the next few minutes. So this is basically the portal that we used to study in our college lectures. So if we check this particular view in the isometric here, so here we can see that basically this beam, this I beam, is connected to this I shape column here, and this I beam is connected to this column flange, not web. For a column, this this projection is called flange, and this straight surface is called web. Let us suppose we make an I section here. So in this I section, this thing that is on the top of this, it is called flange, and this is called web. So this is called flange of a structural steel section, and this is called the web. And you should remember this concept that flange are the part that can have the like transfer the bending moment from beams to column. So can transfer bending moment, and the webs can only transfer shear force, it cannot transfer bending moment. So unless the thickness of web is in the range of, let us say, 25 mm or this 30 mm or 40 mm, only in that case this web can transfer the bending moments also. Otherwise these flanges are the like components that transfer the bending moment. So let us say if a beam is connected, one beam is connected to this flange and the other beam is connected to this web. So this beam can transfer bending moment to this flange, whereas this beam cannot transfer its bending moment to the web. So this connection shall be the shear connection. And this connection shall be the moment connection. So I hope things are now clear to you. So in layman terms or in simple words, the thing that you can like put in your mind to remember is that the connection of the beam when you are connecting it to the flange shall be the moment connection, and the connection with which when you are connecting the beam to the web is called shear connection. So in our case, this connection shall be the moment connections. So along this line all the connections shall be moment connections, whereas along the other axis, that is along this direction, all the connections shall be shear connections. So these connections shall be shear connections. And how we can ensure that these connections shall be shear? By ensuring that the orientation of the column is correct. So here you can see that along this all the connections shall be moment, and along this axis, that is along Z, all the connections shall be shear connections. So we can assign the properties to these beams here. So let us say for right now we can assign IPE 240 only to these beams here. And the reason why we have provided the bracings along this axis is that because shear connection axis is the much weak axis as compared to the moment connection axis. So that is why we have provided bracing along this direction. And as a simple thumb rule, always I shall always recommend you to provide bracing along the shear connection directions. So here like we can see that now we have assigned the properties of the columns and beams, but we have not assigned any properties to the bracings here. So we can go to section database here. Bracings are either of some like double angle or double channel. So let us say we go to British and we can select channel 150, 75, 18, and let us say we like make it as back to back, the spacing of 0.025. So we can left click on add here. So we can select the members here, and let us check the orientation here. So here we can see that this is also looks like an I section here. So the spacing between these two channels is 25 mm, and these two channels are aligned back to back. That is the web of the like both the channels are opposite to each other. So these are called a back-to-back arrangement with the spacing of 25 mm. So right now we have select by missing attributes by missing properties. So we have assigned the properties of all the sections here. So I hope at the end of this lecture the things are clear, that what exactly is the shear connection, what exactly is the moment connection, how we can distinguish between a shear connection and moment connection, how we can assign the properties as per the Europe standards, Europe section libraries or American section libraries, how we can assign the properties of the bracing, and what exactly do we mean by a channel back to back. So in the next lecture we shall learn how we can assign the specifications. So in this lecture we shall learn how we can assign the beam specifications. So in the previous lecture I had already told you that these along the x-axis all the frames shall be the moment resisting frame, and along z-axis all the frames shall be the shear resisting frames. So what we need to do here is that we do need to select all the beams here. So for that we do need to enter beam start, and we need to release my and mz. We do not need release mx because mx is a torsional, like torsional release. So we want that the beams should at least be of that much capacity that it can have the capacity to resist torsion and whatever torsion that is coming on those beams. So left click on assign here, and then again we go to end and my and mz. So now we have released all the beams along the z-axis, and along x-axis all the beams are the moment resisting frames here, and here also we do need to release the bracings also. So I hope now the things are clear that how we can assign the releases here. Basically by doing this, the bending moment for this particular beam shall be like this, and again for this beam shall be like this. But in the case of the beams along this axis, there shall be negative moment also, and there shall be positive moment also. So negative moment shall be on top here and positive moment shall be on the bottom here. So these are the things that you should understand, that as a designer this is your responsibility, that you do need to assign a particular axis for the bending moment release and assign a particular axis for the bending moment capacity transfer. So coming back to this, so now we have assigned the specifications also, and but there are other specifications also that you do need to assign. That is, for the diaphragm analysis we do need to assign a diaphragm also. So we do need to go to node floor diaphragm here, and here height we can enter it as this 3.5 meter here. So we enter the height as 3.5, and we can let the master node information is calculated and define floor lineage as select nodes here. So we can select all the nodes here, and then we can left click on assign to selected nodes and yes. So with this option now we have assigned the fixed diaphragm also here. And after that in the previous lecture I had already studied you, or I had already taught you how the connection or the junction problem needs to be resolved in the STAT software. So if we open this particular junction here in the isometric view, you will see that this thing is going wrong here. That is, this I beam is going inside this column here, and the one more problem is that column is not even going on the top here. The beam is different, column is different, the beam is going inside the column. So all these things needs to be resolved with the help of these specifications itself. So first of all, if we want to resolve this moment resisting frame problem here, so here the property says that the width of the column is 409 mm. So we do need to shift this particular beam by 409 divided by 2. that is, let us say it is 4110, so we do need to move this particular joint by 0.40, this 0.205 meters. So we go to beam and we go to offset and select the offset X as 0.205 and left click on add here. We enter this particular beam here. So if we see now this in the 3D view, here we can see that now the things are correct. That is, this particular beam is resting on the column face itself, and same shall be the case for all the beams here. And here there is the end node here, so we go to beam and offset. Here we need to enter end, and X we need to enter minus 0.205 and left click on add here. So select all the beams here and do the same here. And similarly we do need to offset the starting points here. So now we have done the correction for the beams, but after that we do need to do the correction along for this column location also. So let us check that whatever we have done is correct or not. So here we can see that for columns beam junction everything is okay, except this particular problem here, that the column is not going up to the top here. So the height of this beam is approximately 516 mm. So we can left click on beam here and offset. We can select as end and we can enter Y as 0.260. Left click on add here. And if we now see the junction here, here we can see that now the column is going up to the top of the beam here. So now the details are correct. So basically what we need to do is that we need to select all the beams parallel to y-axis, and we do need to assign this particular specifications. So now like we have assigned all the specifications that we do need to provide. That is, we have assigned the releases, we have assigned the diaphragms, and we have also assigned this offset commands so that our structure looks realistic. So now you can see that the structure is looking much more practical and useful. Although I should confess that most of the people don't do this. Most of the people are like, they just go to center and analyze and design it. And otherwise also STAAD also recommends that you should do this offset commands also. So now we have studied the specifications. After that we have assigned the properties also, we have assigned the supports also, and accordingly we have assigned the material also. After that comes the load and definition command. That is somewhat demanding in the form of you should have a thorough knowledge. So to make the thing simple, what I will do, or what I will explain you in the next lecture, is that for the steel structure there are various options for doing the design and analysis as per the American standards. But American standards are somewhat, I must say, somewhat complicated in the perspective they deal with the structures. So to make the design process simpler, we have a process called direct analysis. So for steel structure, direct analysis approach is most widely used, I must say, when we are designing the softwares, when we are designing the structure with the help of a START software. And seismic definition I had already explained in the previous lectures also. We shall also enter the reference load definition here. After that we shall also enter the wind definitions here, and then we shall enter the load cases and load combinations. But before we start defining these definitions and load cases, I shall explain, or give you a brief up of what exactly do you mean by number 1 P capital delta analysis, number 2 P small delta analysis, and number 3 the direct analysis, and how we do need to take care of each and everything. That is how we do need to do the P capital delta and small delta analysis with the help of this direct analysis option, and how we do need to take care of the notional loads also. So I don't want you to just tell you all these things, because I must say that most of you people must not be familiar with all these terms here. So in the next lecture we shall learn these direct analysis definitions and P delta concept. So in this lecture I shall teach you the basics of P capital delta analysis, P small delta analysis, and direct analysis method, which is also called as DAM in the form of a short form. So to make the things clear, I have opened this RISA manual. Basically RISA is also a very good software for the structural analysis and design, and I must say the best structural references or the best theoretical content to study how a structure analyze and design can be accessed from this RISA help manual. It is available for free of cost. Just Google the RISA help option here and then open the RISA 3D manuals. So here there is an option for P delta capital delta analysis. So and it has beautifully explained the P delta analysis, what basically is meant by P delta. Basically there are two components which we are talking about. One is the capital P, that is the axial force that is acting on this column, and the second thing is the delta. So you should notice that this delta is the capital delta that we are talking about here. So basically the whole concept of this P capital delta analysis is that when we are putting P axial load on this, the column may deflect, and due to this deflection, delta deflection here, it may receive secondary forces also. So to consider those secondary forces, we name it as P delta analysis. So the theoretical definition is given as: when a model is loaded, it deflects, and the deflections in the members of the model may induce secondary moments due to the fact that the ends of members may no longer be collinear in the deflected position. So this is basically the concept that for P delta analysis, the secondary moments may be induced. And why those secondary moments are induced? Because when we are putting the axial load here, the line of action is not collinear with the line of the support here. So these secondary effects for members can be accurately approximated through the use of P delta analysis. This analysis is called P delta because the magnitude of secondary moments is equal to P, the axial force in the member times delta. The distance one end of the member is the offset from one end to the other end. So here we can see that this is basically the simple flow chart that RISA has shown here. That is this undeflected shape. After putting this P, it deflects, and these are the secondary shears that have been developed here. So P delta limitations. So P delta algorithm is based on end joint displacement and will not automatically account for the effect of interior span forces on members or member end rotations. And P delta effects are not calculated for plates. This is valid for START also. And this is also a very important point, that is P delta effects are not currently included in dynamic and model analysis. This is although applicable for RISA, but for START also, when we are doing the dynamic analysis, we cannot use the P delta analysis options. So these are the basic compression only, P delta conversions, and local instabilities, flexible structures. Here comes the stiffness reduction for the direct analysis method, that is DAM method. So although we shall study this direct analysis method separately in the separate PowerPoint presentation, but here the software is saying that direct analysis method requires a reduction in the axial and flexural stiffness of some members. So this is done to account for the non-linear material effects caused by residual stresses. So this stiffness reduction can be problematic during the early stages of design when your member may be smaller, and then they will be after basic drift and stress criteria are met. So although things are not much clear here, so that I will teach you in the separate lecture, but for this particular page that I want you to focus is the concept of P capital delta analysis. That is this is the column. After putting this P, the column deflects, so this is a delta here. So to count for these effects, P delta analysis is considered. After that, P small delta analysis also. So basically this is also a very important concept. Steel structure is a very flexible material. Unlike the concrete structures, which is a very rigid, steel is a very flexible material. So here when we are talking about capital delta and small delta analysis, these are two different things. Capital delta accounts for this particular deformation, that is, this line of action is not collinear to the line of the support. So that is called the capital delta, and small delta is the local effect of curvature here. So P little delta effect is essentially the destabilizing effect of the individual member curvature. That is, these members may not be exactly 100% straight. They may also have some small curvatures along the line of action. So to account for the destabilizing effect due to these undesirable curvatures, we use P little delta analysis. So in practical applications, this is also a very important concept. So in practical application, the effect of P little delta will normally be much smaller than as compared to this P big delta analysis. So the following figure demonstrates a displacement that caused the P capital delta, that is, this is the capital delta and this is the small delta here. So these are the some special things that you do need to understand here. So I hope things are now clear to you that what exactly is the difference between the P capital delta analysis and P small delta analysis. P capital delta is the account for the difference between the line of support and line of action of force, and P small delta is because of the undesirable curvature of the members. And after that we move over to the direct analysis definition. So when we Google the direct analysis AISC, here there is a handout by AISC.org that is available free of cost on the internet, and for that particular handout there is also a YouTube video tutorial here, that is direct analysis method and application. This video uses this particular handout only. So when we left click here, this particular this webinar will open, which explains the application and examples of DAM, that is direct analysis methods. So to start, this is the definitions that is very important. That is, so to start here, it has started with what exactly is a direct analysis method. So direct analysis method is a rational approach to stability analysis and design. So P capital delta and P small delta effects are accounted for through second order analysis. So this concept is valid for STAD, SAP, ETABS, all the softwares, and RISA also. So geometric imperfections accounted for through direct analysis in analysis model or by applying notional loads. In STAD we do apply notional loads only. So notional load itself is a very different concept. So basically notional loads are used by some building codes, and they serve as a minimum lateral load or as an alternative to modeling the actual out of plumbness or out of straightness of the structure. So this is a important thing that you do need to remember. That is what exactly is the purpose of notional load. They are used to model the actual out of plumbness or out of straightness of the structure, which do exist in practical. The structures are never straight, or they are like out of plumb by a minor degree. So instead of changing the geometry of structure, an equivalent destabilizing load is added to the structure. So this basically notional load is followed by ASCE 7, AISC 360, Australian standards, New Zealand standards, British standard, they are also superseded, and European code also. I must confess that around 5 to 6 years back, I had first heard this notional load while designing a structure with the help of a British standards only. So in British standard, the notional load values are quite high, that is 0.5%, whereas in New Zealand, Australian and American standards, they are in the range of 0.2%. And as per ASCE, minimum lateral load of 1% of dead load of structure should be applied at each floor as a notional load. And so basically STAD also gives us an option for like entering the notional loads. But coming back to our point here, so in direct analysis method, notional loads are basically used to account for the geometric imperfections, which is written here. So after that, inelastic effects such as distributed plasticity are accounted for using flexural and axial stiffness reductions. This is also a very important concept, that is in direct analysis method. The flexural and axial stiffnesses are reduced, and the most important thing, which forms the reason of why direct analysis method is widely used, that we use K value as 1. So as per the ASCE 360, effective length factor can be calculated with the help of this alignment chart for side sway inhibited frame, and similarly there is a separate chart for moment frame, that is side sway uninhibited frames. So to avoid all these long hand calculations, so with the help of this particular direct analysis method, we can just design with K equal to 1 only. So here also, why we should use a direct analysis method, because this is a primary method and it's applicable to all types of structural systems. The most like the valid thing that is applicable for lazy engineers like me, there is no need to calculate the K factors, and effective length method is limited, and it is applicable for all side sway amplification values. So secondary order effects are, what exactly are the secondary order effects? The P capital delta and the P small delta that we have already discussed in the few minutes back, and equilibrium satisfied on the deformed geometry. So here also it is again explaining the P and this small delta and P capital delta here, and secondary order effects. So here also we can again see that this is a capital delta and this is a small delta. So this is also a very good figure to to explain you. So this is basically small delta here. So for this small delta, this P delta moment will generate, and for this capital delta, this P delta moment will generate. So, and these are the primary or first order bending moments. So this plus this gives us the total bending moments. So in each in each and every structure, when we are doing the also considering the secondary order effects, so in order to the first order bending moments, the P capital delta moments and P small delta bending moments will be added to give us the final bending moment profile here. So here also it is the first order deflection, that is HL³ by 3EI, which we used to study in our textbooks, but this is a secondary order deflection graph here. And if we want to consider the things between the direct analysis method and effective length method, so effective length method can also be used for secondary order or amplified first order. The member stiffness that we use is the EI or EA, but in the direct analysis method or DA method, we use the reduced EI and EA, that is stiffness and area. Notional loads, we use it at 0.002 minimum percentage. And column effective length we need to determine, whereas in this method we can go ahead with k equal to 1. So these are the graphs to compare between the direct analysis method and traditional effective length method. So in effective length method we are around here, whereas in direct analysis method we are around here. So from this to this. So in short, we can conclude that when we are considering the effective length method, the notional loads are not being applied here. The EI and EA, they are 100% here, whereas here they are reduced. So basically all this leads to the increased moment demand. And here also this graph is shown here to compare between the traditional effective length method and direct analysis method. So what exactly are, again all those points are repeated, that is accurately model the frame behavior, factor loads are there, LRFD or AST both can be used. It also consider the initial imperfections, that is 0.2% of notional loads, and reduce all stiffness that contributes to the stability of the structure to account for the severe effects. And second order analysis can be considered. K equal to 1 can be used for the member design. And serviceability checks use unreduced stiffness. So that is also a very important concept here. So this is just I think an example that has been given for your consideration. And what is the purpose of notional load? Again, they account for the geometric imperfections that we had already studied in the RISA help manuals, and applied in the direction that adds to destabilizing effects. So this is just a small example that has been considered. So this is basically the window of the SAP 2000 software, and in ETABS also they do provide this option of adding notional loads here. So if you have a SAP 2000 licensed software, then you can also do the analysis as per this particular handout. So here you can see that the area is reduced by 0.8 EA, and EI, that is stiffness, is reduced by 0.8 tau B EI, and tau B is always less than or equal to 1 when alpha pi by py is less than or equal to 0.5, and this tau b's values is 4 times alpha pi by py for this equation and for this equation. So here this SAP 2000 gives us an option of tau b adjustment. So here this is a small p delta and this is a capital P delta. So much has been said and much has been written about the P capital delta and P small delta analysis. So you don't need to worry about much that how you can do this direct analysis method of P capital delta, P small delta. So that I will explain you in the next lectures. But it shall be good if you can model this particular structure in either STAD or SAP 2000 software, and just check the theoretical and practical results, so that things shall be much clear on how to use the direct analysis method approach. So in the previous lectures we have learned what is the basic of direct analysis and what are basically the basics of P delta analysis. So in this lecture we shall define first of all the direct analysis method definitions. So in this StatPro software, you will see that under the case of general and load and definitions, and under the definition there is an option called direct analysis definition. So if when we need to left click here and then left click on add here. So here you will see that there are various parameters here, that is flex parameter, FYLD, axial and notional load factors. And notional load factor is a term that I had already explained in the previous lectures. So axial parameter FYLD, that is yield strength, and flex parameter, that is flexural parameters. So when we refer to the help manual that is already provided in the StatPro software, so here you will see that under the direct analysis, so the AISC 360 2005, although it is also incorporated in 2016, so it accounts for the second order effects resulting from the deformation in the structure due to applied loading, imperfections and reduced bending stiffness of members due to the presence of axial loads. So this is basically non-linear iterative analysis, as the stiffness of the members is dependent upon the force generated by the load, and the analysis will iterate in each step, changing the member characteristics until the maximum change in any tau b is less than the tau tolerance. See, this is the basic term that I had already explained previously many times. Second thing, it is a non-linear iterative analysis that you already know. And how we can say that it is a non-linear iterative analysis, as the stiffness of members. Stiffness is basically the modulus of elasticity into the moment of inertia, E into I. It is dependent upon the forces generated by the loads. So how the analysis will be performed? So the analysis will iterate in each step, changing the member characteristics until the maximum change in any tau b is less than the tau tolerance. So this line is also very important line. So how this line is incorporated in the software, for that basically we do need to go to analysis command, and here you will see the perform direct analysis option. So here you will see find the tolerances, that is tau and displacement. So the line that we are studying here, that is the analysis will iterate in each step, changing the member characteristics until the maximum change in any tau b is less than the tau tolerance. Notice that this tau tolerance is the value that we are providing here, that is tau tolerance here. So either we can enter it as 0.001, that we will do in the separate lecture, but confining ourselves to this direct analysis definition only. So here we do need to first of all enter these 4 parameters. So this is basically the importance of this line. And after that, if any maximum change in any tau b is less than the 100 into tau tolerance, and the maximum change in any displacement degree of freedom is less than the displacement tolerance, that is in this option here, basically there were 2 like tolerances, that is tau tolerance and displacement tolerance. So the software is saying that the maximum change in any tau b, let us say maximum change in any tau b is 0.01, is less than the 100 into tau tolerance, and the maximum change in any displacement degree of freedom is less than the displacement tolerance also. So both of these parameters are the threshold for which the software will consider whether the solution has converged or not. So this is basically the thing that will keep on repeating, and how we can make sure that the software will do the iterations. So here we can enter the iteration, let us say 100. So right now I am not focusing on this window, but there are 2 steps involved in setting up a direct analysis. Number 1 is to specify the definition with the define direct command, and number 2 is to specify a direct analysis method with the command perform direct analysis. After that, these 4 are the parameters that we do need to enter in this option here. So here you will see that number 1, flex parameter. So flex parameter is nothing but it is the identification of members whose flexural stiffness is considered to contribute to the lateral stability of the structure, along with the initial value of tau b that should be used. and members listed with flex will have their EI, that is stiffness, factored by 0.8 times tau b while performing the global solutions. So the final member forces and code check will be with 100% of flexural stiffness. So the final member forces and code check will be with 100% of the flexural stiffness. So that is basically the definition of the flex, and by default this value needs to be entered as 1 here. So we need to enter a flex value as 1 here. After that, FYLD. FYLD is basically the yield stress of the members that is used only in the calculation of tau b. So in our case, the flexural stiffness of the members is basically 345 Newton per mm square. So for the units kilonewton per meter square, we shall enter 3,45,000 kN per meter square. So left click on add here. After that, axial parameters. So for axial parameter, basically no data is required, but the axial parameter means that we do need to identify the members whose axial stiffness is considered to contribute to the lateral stability of the structures. So in our case, basically the axial parameter should be assigned to all the columns, and these members will have their EA factored by 0.8 while performing the global solution, and the final member forces and code check will be with 100% of the axial stiffness. That is the same line that has been written here, except here was the flexural stiffness and here is the axial stiffness. And notional load factor, we have already studied and discussed much about the value of this notional load factor for the American standards. So it shall be 0.002. So we shall enter this value also, that is 0.002, and left click on add here. And after that, when we left click on this plus sign, here we can see that axial parameter is not defined. So left click on add here, and after that we basically need to select the columns here. So select beams parallel to y-axis. Accordingly, we shall assign axial parameters to all the columns here. By default, notional load factor is applied to the whole structure, and FYLD 3,45,000 and flex parameter 1. So we shall assign all these parameters to the columns. So select beams parallel to y-axis and assign to selected beams, and after that FYLD 345. Again, beams parallel to y-axis. So what basically this again the direct, and this it is explaining the graphical user interface for adding these direct analysis definition. So these parameters can be then be assigned to the required members as with the other loads or definition commands. And after that, this is basically the definition only, and to do the direct analysis, we do need to assign the analysis command from this option here, and then we need to enter the perform direct analysis, and only after that the start will perform the direct analysis correctly. So this is just you can go to start help manual and search for flex, then only you can find this page. If you have this software with you, licensed software with you, then you shall have this help manual with you also. So now basically this we are finished defining the direct analysis definitions. So now we shall study how we can assign the seismic definitions also. So we can left click on seismic definition. Here in this lecture, I shall try to teach you how to define the seismic parameters as per IBC 2012 and ASCE 710. Although I have explained all of this in the previous lecture also, but just for your clarity, I shall explain all these things again to you. Here start can basically define the SS and S1 parameters. SS is nothing but mapped MC for 0.2 second spectral response acceleration, and S1 is mapped MC for 1 second spectral response acceleration. And as per the zip code, latitude and longitude, stat can tell you the value of SS and S1. So that is why these values are highlighted in this yellowish orange color, cause it do depends on the zip code only. So when we enter 92888, it is non-standard zip code. So 92. So if we like enter the wrong zip code here, then it will automatically be locked here. So what we can do is that we can again open this option here, again type IBC 2012 and zip code 92887, and when we search for zip code 92887 belongs to this Yorba Linda, California map. So what if we want to do the like design for the New York City? So we can go to ATC Hazards Council, hazards.atccouncil.org. Here we can search by address. Let us say if we want to search for the New York City. So for New York, this is the location over which New York is situated, and as per the ASCE 710. So basically the wind speed is given here. That is, if we consider want to consider the MRI of 50 here. So the speed is 90 miles per hour, and if we want to consider the snow here, as per ASCE 710, we need to consider 20 pound per square feet. And if we want to consider the seismic parameter here, reference document shall be ASCE 710. Risk category we can select it as risk category 2. Site class we can select it as very dense soil and soft rock. So for that, it was automatically calculating that SS is 0.278 and S1 is 0.072. So how we can assign these SS and S1 values for our structure? So we just select the cell and press delete option on the keyboard. So you will see that this option can also now be removed, and this option automatically open. So SS in our structure is 0.278 and S1 in our structure is 0.072, and TL is long period transition period. So TL value can be taken as 6. For seismic design category V, NFA, NFE, CRS, CR1, PGA, all these values are given here. So going back to our model, we can select TLS 6. Importance factor we can select it as 1, and RX for this type of structure we can select it as 4.5. Although I shall suggest you to go to this ASCE 710 code and go look for this RX and RZ value, and after that SEL, FA and FV. So FA is 1.2 and FV is 1.7. So basically these star values are the optional values here, and X value we can enter it as 0.8. So you can refer to this exponent used in equation and this and refer table 12.8.2 for ASCE 705. I don't exactly remember the X value, but as per my experience it should be in the range of 0.8 here. So basically now we have entered all the data here, and if we want to see whether some data is missing or not, so all the data has been entered, and do remember that we have selected risk category 2 and site class as C, that is very dense soil and soft rock. So here basically we have these 6 site class here. So these 6 site classes are nothing but A, B, C, D and E and F. So here we have chosen the C, that is third site class. So we do need to enter 3 here, because otherwise the behavior shall be different. So left click on add here, and we can select it as self-weight factor as 1 here. So now we have defined the seismic parameters for the New York City also, and after defining the seismic definitions and direct analysis definition, we do need to define the wind as well as the reference load definition, but that we will do in a separate lecture. But for this lecture, as we have already calculated the this wind and snow loadings, so we should save this loading in our model. So do remember that we do need to consider 90 miles per hour, and snow we do need to consider 20 pound per square foot. So coming back to our model here, so we can left click on add here. First of all, as I had discussed in the previous lecture also, that you do need to enter the EL earthquake parameters here. So we enter ELX, after that ELZ, after that we need to enter dead load, live load, after that we need to enter the snow load, after that we do need to enter the wind loadings, that is WLX, WL minus X, WLZ, and WL minus Z, that is wind direction along all the 4 directions. And after that we can enter the temperature loading also, that is TL plus and TL minus. So all the loadings has been now considered, and after that when we left click on this ELX, so you will see that seismic load options are now open. So we can enter X direction, and here vector is 1. So left click on add here, and after that again we can enter the seismic loads option here, and Z and add. So now we have defined the seismic load cases, and after that we shall define the dead load case. So we do need to enter factor here as -1, and left click on assign to view and yes. And there's this thing that you should understand, that we should always add 10% when we are designing steel structures. 10% is for all the connections weight that shall be installed on the steel structure. So some people take it as 1.05, some people take it as 1.1, but as per my recommendation, always take 10% extra, because connections weight do themselves contribute to the 10% of the total weight of the steel structures. So now the dead load has been defined, and similarly we can define the live load also on this top floor here, but that we will do in the next lectures. But in this lecture my focus was that I should explain you what basically is the system with which we can define the seismic definitions as per the IBC 2012, and how this website hazards.atccouncil.org helps us in not reading the long codes, and just helping us to give out all the seismic and wind and snow and tornado parameters. And most important one was that how we can enter the direct analysis definition, and how this perform direct analysis command is entered. So in the next lecture we shall what we will do is that first of all we shall define the wind definitions, and after that we shall define the reference load, and after that we shall enter all the data here. So in this lecture, first of all we shall learn how we can define the wind definitions. So wind definition has already been explained in the previous lectures by me, that how you can assign automatic wind load generation for the RCC structures, for the steel structures. So as this is a steel composite structure, so first of all left click here, and then left click on add here. We can enter comments as WL X here, and windward. After that we can add WLX leeward, and then WLX sidewall. Similarly we can enter WLZ, windward, leeward, and sidewall. So now we have basically six type of wind definitions here, and we should know what exactly is are the dimensions of the structure here. So the along x-axis, the length of the structure is 14.5, and along z it is 15.75, and the height of the structure is 3.5 meter. So as in the previous lectures, we have learned that how we can calculate the approximate natural frequency of the structure also. So the natural frequency of the structure can be approximated for structural steel moment resisting frame buildings, like in our case as this 22.2 divided by h to the power 0.8. So h in our structure is 3.5 meters. So opening the calculator here, so 3.5 to the power 0.8, it comes out to be 2.724. So 22.2 divided by 2. So opening the calculator here, basically now we need to calculate this natural frequency with the help of this formula. So 3.5 to the power 0.8 is approximately 2.724. So 22.2 divided by 2.724, it is approximately 8.15. So the natural frequency of this structure as per this for structural steel moment resisting frame buildings with the equation 26.112 is approximately 8.149. So we do need to go to this type 1 here, left click on add here. Here we can refer to this calculate as per ASCE 7, and here we can enter the building classification category. Basic wind speed as per the ASCE 710 is approximately 90 miles per hour for MRI 50 years. So here we can enter 90 miles per hour. Exposure category we can select it as B, and structure type as building structure. Left click on apply here. After that, main building data. So main building data, first of all we can enter the units as meter here, and here the building natural frequency, here we need to enter 8.149, and building damping ratio we can select it as 5%, and enclosure classification we can select it as open building. So building height is approximately 3.5 meters. Length along the direction of wind for WLX is 14.5, and other direction is 15.75. So left click on apply, and building and design pressure for windward is approximately this 7.024 pound per square foot. So left click on apply and OK. So this is basically the WLX windward, and then left click again on add here. We can assign to view. Again after that we can enter WLX leeward also. So again we repeat the same procedure here. Basic wind speed as 90. Exposure category, structural type as building structures. Main building data we can select it as meters here, and natural frequency 8.19. Enclosure classification we can select it as open building, and height as this 3.5. Length along direction wind is 14.5, and this as 15.75. So left click on apply here, and building design pressure for levered is again the same value here. So for levered it is minus 4.4. So left click on apply and OK here. So left click on add here and then factor 1 here. After that we need to again repeat the process for the side walls. So left click on this calculate as per ASCE. (14.5), 3.5, 14.5 and 15.75, 8.19, damping ratio is 0.05 and structure is open building. So building design pressure for side wall is in the negative, that is minus 6.15. So left click on apply and if we select this G value here also again, then the value remains same, and left click on add here. Factor we can enter it as 1. After that again we need to enter the WLZ for this windward side. So calculate as per ASCE. Notice that building length along the direction of wind for WLZ is 15.75 and this is 14.5. So now we have defined all the wind definitions, and after that we do need to define the these dead load cases here. So basically dead load may be the load that may act on the top of this composite deck, but before that first of all we do need to name this whole structure in the form of a group. So in the previous lecture I had already told you the advantages of using the group command. So press Ctrl plus G option on a keyboard, name this group as G1, select type as floor, left click on OK and select all the beams here and left click on associate. So now we have basically defined a group G1 here. So now basically when we left click on dead load here, we can go to this flow load option here and then we can left click here as group, and here basically the D1 was already defined here, so we can left click. Let us suppose the finishing load on the top of this deck slab is minus 1.5, and this is basically the one-way distribution that we are talking about. So left click on this add here. So this is somewhat a complicated problem here. So after defining the group command, we shall left click on DL option here, and then left click on add here. Go to flow load option here and group, select the G1 that we have already defined, and select, suppose the finishing load on the top of this composite deck is minus 1.5 kN per meter square. As this is a one-way load distribution, so we shall select one-way distribution, default towards longer direction, and then left click on add here. So with this simple method, you can apply this flow load, one-way flow load over the top of this composite deck system. And then after that, let us suppose the live load on the top is 5 kN per meter square. So we again go to this flow load option here and then group, and then again we select it as -5 and one-way distribution. So now we have defined the live load also. And snow load, we have already considered that snow load for the New York area is 20 pound per square foot. So when we search for this 20 pound per square foot, it is approximately 100 kg per meter square. So we can just go to the snow load option here and then left click on add here, flow load, group, and enter it here as -1 kN per meter square. So now we have defined the snow loading also. And temperature load, we can just go to left click on add here, and then here we will see that there is an option called temperature load, and temperature change for axial elongation, we can select it as 30 here. And as this is a positive temperature change load, so we select plus here, and for this minus option here, again go to the temperature load, and here we can select it as -30. And after that, the most typical part, that how we can define the wind loads. That considering this whole structure is an open structure, so STAD gives us an option that we can generate the loadings for an open structure also. So left click on WLX here, and here opening the wind definitions here. First of all, if you want to consider the windward load case here, so the windward load case shall apply from this point to this point. So X range shall be 14.4. So we go to the wind load option here, and then X, type 1 only as this WLX and windward, and we can select the X range as 14.3, and then left click on open structure and add, and right click on labels, scales, apply immediately, and decrease this value here. So now we can see that the whole this on all of these members, positive WLX windward wind definition has been applied, and after that this for WLX only we shall apply the leeward load case. So we again go to the wind load, select type as 2 regular, and here we need to select this leeward sidewall face, and X range we do need to enter here as 14.4 to 14.6. Left click on open structure and add here. So here we can see that this load is acting in the opposite direction, so we can enter the factor here as -1. So now we can see that now all the loading is acting from left to right. And considering the side wall combinations also, so the left click on this add option here, wind load, and here we can select it as leeward sidewall face, and then left click on open structure and add. So here we can see that the directions are not much clear as they are required. So the X range for this sidewall face is basically this Z is up to at 0. So here we can see that the sidewall load cases are applied, and similarly we do need to apply the sidewall cases here also. So now we can see that we have applied the load cases for all the that is windward as well as for leeward as well as for sidewall for the wind load along the plus x. So similarly we shall apply the wind load for the minus x also, wind load for the plus z also, and wind load for the minus z also. Now considering all these shall be reversed here. So WL for WL minus x, basically this shall be the windward phase and this shall be the leeward phase. So x range shall be from 14.4 to from 0 to 14.5. So this is the wind load acting from WL minus x here, but it shall not act on this point here. This is the considering this is the leeward phase here. So this is basically the windward phase forces, and these are the leeward forces. After that we shall apply for the side walls here also. So now we have applied the all the wind loads for the WL minus x also. So similarly we do need to apply the wind loads for WLZ. Consider this is the windward and this is the leeward phase, and these are the sidewall phases here. So basically there's one error that we are continuously doing here. We are not changing the type 2 here. So here in this case, this is basically the sidewall case. So we do need to select this 3 type here, and here it should be again type 3. This is an error that I had done because I was not paying attention to this particular clause here. So for WL minus x, this is type 1 is okay for considering this is a windward, and after that this is the leeward load case that we are talking about. These are the sidewall load cases. So now the forces and directions are correct, and the types are also correct. After that, when we are talking about WLZ, windward phase, so we need to select fourth wind type here, and now the forces are correct. And after that, this is basically the leeward phase, so we need to select Z as 15.6 to 15.8 here. So here we need to select this type 5 here, Z 15.6 to 15.8 open structure. And after that, we do need to apply the sidewall loads also. Similarly, we can enter WL minus Z combinations also. So now we have completed applying all the wind loads and as per all the wind definitions. So I am repeating here what exactly we have done here. So basically we have defined all the 6 types of wind load definitions, and accordingly basically wind loads can categorize as wind load along this plus x, wind load along minus x, wind load along plus z, and wind load along minus z. But when wind will strike along this x direction, some of the wind component may travel through this part also, but the the wind that will act on the sidewall will be very less. So although practical, if you are if you will talk to me regarding the practical aspects, I shall advise you that you shall only apply wind load along this direction only. There is no need to apply sidewall wind loads here. But just to make the things clear to you, and in this case structure is open, but in your case the structure may be enclosed or partially enclosed also. So in that case what can you do? So for helping you out in those cases, that is why I had categorized into various types of wind loads and various type of wind load definitions here. So it's like applying the load, but knowing that the sidewall wind load shall not go on the design. But just for your clarity, I have applied these loadings here. So as a checklist, we had already applied wind definitions, seismic definition, direct analysis definitions. We have applied all different types of loads here also. So after that we shall apply the reference load definitions also. So but before that we should also do one important step here, that is after IBC load x1 you should enter perform analysis and change. So some of you must be familiar with the start software. So if you are not entering this command here, then you must be getting an error that if this UBC analysis has a tension or compression. So to avoid this warning, you need to enter perform analysis change after this IBC load x1 and after defining the seismic load along z-axis. And after that we shall generate the reference load definitions also. So left click on add here, loading type we can enter it as this mass here, and we can name it as mass source. Left click on add here, and we can add the self weight along all the 3 directions here. So we can enter self weight x1, and if we just copy paste this whole arrangement here. So basically these are the different loads that needs to be entered in the mass source here. Self weight we can enter it as 1.1. Replace it with y and z, and this we can enter it as flow load, and just save this option here and go to this reference load definition here. Left click on add here. So here we have this option of flow load. So group, and the name was G1. Here pressure we can enter it as 1.5 for the finishing load, and after that we can enter the live load for live loads also. So if the as the load is approximately 5 kN per meter square, I have not applied any deduction here just to be on the conservative side. So now all the mass source definition has also been defined. So now we shall learn how we can define the load combinations here. So in the load combinations, if we have this auto load combination here, we can select the code AISC and we can select the general and generate loads here. Now the thing is that you shall see an option where it is asking that whether we want to create repeat load cases and if we want to include the notional load. Notional load I had already defined you, but what exactly is this repeat load case command? So this is also a very interesting concept that most of the STAAD users don't know. Website of STAAD, they have generated a different like a unique post just to explain the difference between the load combination and a repeat load. So basically the load combination and repeat load are two different things, and the difference lies in the STAAD goes about calculating the results. So when the STAAD is calculating joint displacement, member forces and support reactions, for a load combination it just simply algebraically combines the result. That is, let us say for two cases is 100 plus 50, so it shall give you just 150 as a result. But in for the repeat load, the procedure followed is that what occurs for the other primary load case. So in simple words, the load combinations gives you the scalar result and repeat load gives you the vector result. So for a repeat load, a load vector P is first created and then that load vectors gets multiplied by the inverted stiffness matrix to compute the displacements. Whereas in like in load combination, it just algebraically combines the results. So here also it has given another example. So in other words, for example, in order to obtain the results of load case 10, it has no need to know what exactly constitutes the load cases 3, 4 and 5. It just needs to know what the results of those cases are. So the structure is not actually analyzed for a combination load case. So this is a very important line that you do need to understand. That is, in load combination, it is not a different load case, but for repeat load, the STAAD consider it to be a different load case. And in simple words, if you are still not clear, it is just a scalar sum and it is the vector. It is not it's not basically a vector sum, but it is just a vector mathematics of a different load case. So this is just like this, it is available free of cost, but I have attached PDF of this page also in the attachments. So now I hope the things are clear to you. So when you see this repeat load case option, though this option will not look an alien to you, so load combination code shall be as per AISC. We select the general arrangement here, and here you like you can see that various types of load combinations are being presented in front of you. So 1 times dead load, 3, 1, 4, 1, 10, 1 and 11, 1. That is dead load plus live load plus 10 and 11. That is the temperature loadings here. So this is not a correct load combination, or we can enter it for the adverse effects also. So 3 and 6, that is dead load plus wind load. And for 1 and 2, that is ELX and ELZ, the software has considered both plus as well as the minus load combinations. And here we can just go ahead with this create repeat load case and then left click on add here. So now I hope the things are clear to you. That is how we can generate the load combinations. And if we want to do the floor vibration analysis also, see, basically when we are talking about the composite deck system, floor vibration is a very important concept that you do need to understand. Basically when as this is a like a lightweight arrangement, not unlike the conventional beam and slab system which has its own very high self weight. The self weight of this type of structure is very like somewhat lesser as compared to the conventional system. So in that case, basically what happens is that the due to the like movement of the persons on the top, they may experience some vibrations. So the code guides us that you should make sure that the vibration that occurs on the top of this composite deck system should not be uncomfortable. So for that, AISC has issued a separate like guideline for that for the calculation of this vibration. So the STAT also gives you a floor vibration report that we will discuss in the next lecture, in the separate lecture. But right now we should add a load combination for the just for this vibration analysis. So basically 3 and 4, we just want to add 3 and 4 here. So it shall be good if you can just go to the editor file here. And name it as 101 and name it as floor vibration. And 1 times dead load plus live load. So here also you can just like ignore the negative temperature load case, because I don't think that it will go on the design. Just to make the thing simple, I am considering this plus temperature or plus load case only. So you can name these load combinations also. So like this is 1 times dead load, this is 1 times dead load plus live load plus temperature load. This is 1 times dead load plus no load. This is 1 times dead load plus 0.75 times live load plus temperature load. So accordingly you can name all these load combinations so that you can like easily check the results. So after that we have added all the load cases and all the load combinations. So in the next lecture we shall learn how we can do the analysis. We can enter the analysis command and how we can enter the design commands. So as a checklist, we have entered all the properties for our structure, and we have entered all the specifications, and we have entered all the things so that structure looks exact real. Like we have corrected all the end like junctions here, and we have now assigned the supports also. We have defined the load definitions, we have defined the load cases, load combinations also. And after that we shall define the analysis command. As this is a direct analysis, so we should enter perform direct analysis, and there is this option that is LRFD and AST. LRFD is nothing but load resistant factor design, which we also call it as limit state design for in some countries. So although the limit state concept and LRFD concept is somewhat different concept, but in layman terms I should say that this is the method which used the factored load combinations, and this is the like method which used the this 1 times or 0.75 times the something like this load combinations. So in our case we have selected AST. Tau we can enter it as 0.01, displacement we can enter it as 0.001, and number of iterations we can enter it as 100. So these options we have already studied in the previous lectures. That is what exactly the significance of this tau tolerance and displacement tolerances. So left click on add here. So now this direct analysis command has been entered here, and after that we shall enter the design parameters. So in design in steel, here we can see that AISC 360 AST option is coming here. So left click on define parameters here. So here you can see that there is a long list of parameters that needs to be or checked and entered here. So first of all, we shall go ahead with CB value. So CB value we can enter it as 1, and after that we shall enter UNB and UNT parameters here. So UNB, that is unsupported length of the bottom flange for calculating bending capacity. Same is the unsupported length of the top flange for calculating bending capacity. So unsupported length we can enter it as 0.5 here, and similarly for UNT also we can enter it as 0.5. After that we shall go to the CMP command. So here basically the composite command, in here we do need to enter the ignore positive moments during design, and after that we do need to go to this diameter command. So dia command we can find it under this con dia. So diameter of shear connector we can enter it as 0.019 mm, meters. So after that we do need to enter the HGT command here. So height of shear connectors we can take it as 0.12 meters, and after that we do need to enter the CYC command, that is cycles command. So cycles we can enter it as the same number only, and after that we do need to enter the DR1 command. So DR1 is nothing but ratio of moment due to dead load applied before concrete hardens to the total moment. So DR1 we can enter it as 0.4 only, and after that we do need to enter this width command here. So here by default the width value is 0.25 into member length. So if we check what exactly is our union like the width, so here we can go ahead with 1.825 into 0.25. So it is coming out to approximately 0.45625. So 1.825 into 0.75. So we can enter it to be approximately 1.375, and after that we do need to enter this FPC command. So FPC is nothing but the grade of concrete at 28 days. So we can enter it as 25,000 kN per meter square. And after that there are other commands also, like the rib height, rib width. So rib height we can enter it as 0.046, and rib width we can enter it as 0.105, and thickness we can enter it as 0.099, that is 99 mm. And after that we can enter this FYLD also, that is yield strength of steel. So basically we have two types of structural steel here. One is 250 grade and the second one is 345 grade. And after that let us see whether there are other commands also. So here we do need to enter the rolled section also and welded section also, because we have both type of sections in our structure. Here we can enter it as shoring as temporary shoring during construction without shoring. And this LZ command is also a very important command for in our case. So basically we have two types of span here. One is the 7.25 meter and the other is 5.5 meter. That I shall explain you shortly. But 7.25 and 5.5. KZ value we do not need to enter because we are doing the direct analysis. Otherwise, STAD also has an option to calculate this KY and KZ value. So this is basically the electrode that is used for the reinforcement openings. This is 60137018. If you're a site engineer, you must have this exposure of these type of electrodes. So now we have basically defined various type of these design parameters here. CB is nothing but the we can assign it to the whole structure here. UN, B and UNT, this is basically the unsupported bottom flange and unsupported top flange. Considering the top flange of all the beams are tied to this composite deck system here, so we can enter unsupported this bottom flange only, because otherwise the top flange is by default this supported. So we do need to delete this command here, and UNT we can enter for all the beams. And after that, this CMP command. So for CMP command, we do need to select these IP sections itself. So we can assign to the whole view here. Dia we can enter for the deck system on the top. So dia this is basically the diameter of the shear connectors, height of the shear connectors after welding, CYC, that cycle of the maximum stress that shear connectors can take. DR, this is also valid for the floor itself. This is also valid for all these members here. FPC concrete compressive strength of concrete at 28 days. So here we basically do need to we do need to apply the FPC commands to these members itself. So we can just copy paste these members here, and then just again go to the edit list and assign them. So rib height also needs to be assigned to these members itself. Same case here. And FYLD 25,000 needs to be applied to these small members itself. And we can go to this bracing members also. They also are in the grade of 250 itself. And we can just go to select by inverse and inverse beam selection, and we can assign to selected beams and yes. And after that, STP 1 and 2. So basically all these sections are the welded sections, so we can assign these commands, and after that we can go to select by inverse and inverse beam selection, and these are the hot rolled sections. Temporary shoring during construction. Without shoring, we can select all the beams here. And this is a very important command that most of the new people are often confused that what exactly is this LZ command here. So basically the problem with STAD is that we do need to feed every data in the software. So if we are talking about let us say this particular panel here. So in this particular panel, if you will by pressing Ctrl+2 option on your keyboard, you can switch on to this isometric view. Basically the length of this beam is from this point to this point. So but in STAD, if you will see the original view here, there are various nodes here. So STAD will by default considers that for this member the effective length value in Z is only from this point to this point, whereas we do need to tell it that this member is a single member from this point to this point along Z axis. but along x-axis, that is along its on minor axis, the member is breaking after each and every distances. So that is why we do not need to apply ly command here, because otherwise also the ly is 1.6075 as per STAD also, so we don't need to apply that manually here. But we do need to tell the STAD that the length of this beam is 7.25. You do not need to take it only from this point to this point. So that is why similar is the case with this along this direction also. But as there are no joints here, so we do not basically need to define the 5.5 LZ. So we can just go to select beams parallel to x-axis and just define LZ 7.25 here. So all these are the strength parameters that we have studied for the composite structures. But after that there are deflection parameters also. So most of the people are often confused with this DJ1 and DJ2 command. So that we shall discuss after doing the strength analysis. But right now our focus should be that all the direct analysis command has been given, design commands have been given. So in the commands we can go for check code and takeoff. So we left click on the steel takeoff and assign to view, and here also. So now we are done with the whole process of entering the design parameters and entering the analysis parameters. So in the next lecture we shall learn how we can design and how we can check the design results and how we can optimize the structure for our consideration. So in this lecture we shall learn how we can do the analysis and how we can design the structure. But before that, there's this one thing that we have missed, that we have not copied these dead loads and live loads in the seismic definition here. So what we can do in this case is that we can add a dummy load here, because basically the problem is that the STAD seismic definition does not accept this one-way definition in its own floor weight. So what we need to do here is that we can go to group here, G1, and we can enter it as -1.5 here, and then left click on add here. Basically the only thing is that we can get the syntax in this form. So we like go to the dead load option here. We can just cut this option from here, and then we can just copy paste this in the seismic definition option. So here we do need to enter the seismic definitions. So here we need to enter the floor weight here and F load as 1.5 and remove the GY. Similarly we do need to enter the live loads also. So we can enter the 100% live load for the conservative side only. So now we have assigned the seismic definition correctly, and after that we you need to go to analyze and run analysis. So here we can see that in the initial run we are getting 1 errors and 32 warnings. So left click on view output file. So here we can see that the STAD is showing that the member 22 has composite property assigned to it, and hence the material constants are set as those of steel. Current specification is ignored except damping ratio. Although this warning is not warning that may harm your structure, but to remove this warning, what we need to do is that we need to go to the editor file, and here we need to search for the constants material steel all. So just cut this option from here and copy paste this option before we define the member properties. So after that again do the analysis. So now we can see that the warnings are now removed, but there is this one error, that is no reference load case of type is defined for mass modeling. So this is just like a typical error that do occurs when you are defining the reference loads and this flow diaphragms. So go to the reference load definition. This is basically the reference load definition. From defined reference load to undefined reference loads, we search for the flow diaphragms here. So the flow diaphragms is defined here, so we do need to define the reference load before flow diaphragms. So again do the analysis, So here we can see that now the analysis is again showing one error. So the error here is approximately this above line contains erroneous data. So this error is basically saying that the primary load case can only be added if set NL command is used. So basically the problem is that we have defined a large number of load cases with the help of repeat load option. So that is why we do need to enter the set NL command in the editor file. So go to the editor file here, and after input width 79, go to set NL. Here we can enter, let us say, a very high number of load cases, that is 150. So this command says that maximum number of load cases that can be in this stud editor file is 150. So we close this editor file again, and again we analyze the structure. So here we can see that now the analysis is being done without any errors. So now we are getting 27 warnings here. So just go to the editor file here. So basically some members are failing in the design, that is IPE 240 is failing. So when we are checking the design here, so here we can see that that it is failing by a very wide margin. So what we need to do is that we do need to increase the size here. So as per this star, it is showing that this IP section is failing in the design, but basically there is a small mistake that has been done in this model. The basic mistake that is done is because in geometry section, when we were defining the composite deck, basically we have instructed the stat that all these beams are composites. So these beams are not the ones that needs to be designed for the composite section, but these are the beams that needs to be designed for the composite section. And how you must be wondering how I can say that this is designed for a steel section and this is designed for a composite section, because when we are double clicking here we can see that the composite property is being considered, but when we are double clicking here, only steel design is being considered here. So this is an undesirable practice that has been done from my side only. So I shall request you that what we basically need to do here is that we should now go to this geometry composite deck and go to this D1 here and just delete this deck here. So after that, the safest practice that you can or the good practice that you can do to define the deck is that just first of all select all those beams here and then left click on create new deck here. So your deck shall be from this point to this point here. We can name it as deck 1. Left click on OK. So now if we see that what exactly are the beams on which this deck is defined, so these are now the correct beams. So after that we do need to enter the data here also. So concrete thickness above fluids is basically nothing but 0.099, and unit weight of concrete we can enter it as 25 kN per meter cube. Grade we can enter it as 25,000, and rib width we can enter it as 0.105, and rib height we can enter it as 0.046. Stud diameter we can enter it as this 0.019, and we can left it as unshored. So we can left click on update deck property. After that again we left click on this create new deck option and we select the deck like this, name it as deck 2, left click on OK. So for this deck 2 we again enter the same data that we had entered for the deck 1. Unit weight of concrete is 25, grade is 25,000, rivet 0.105, height as 0.046, 0.019 and unshored. And after that again we left click on this create new deck option. But before that, please save the model here and left click on create new deck. We can name it as deck 3 and let us check that whether the beams are correct or not. So here we can see that all the desired beams are selected. So here again we enter it as 0.099, 25, 25,000, 0.105, 0.046, straight length 0.019, diameter meters 0.019 and length is 0.12 and unshored. So we can left click on update deck property, and in deck 2 we do need to enter it here as 0.12. Same here. So if we check all the deck properties here, so all the properties are now correct. So save the model, and again we repeat the exercise, that is analyzing and designing. So this was just a small concept that was missed in the earlier lectures, that we do need to take care that these beams are the one that are composite, not these beams, because these are the main beams, but the main loading that is acting are on these particular beams here. So there are 0 errors, 0 warnings and 3 nodes. So let us check that whether the nodes are of some significance or not. So the nodes are of not much significance here. And after that, when we double click here, so here we can see that now it is showing as the composite property. So in this composite property, it is showing that there is no shoring construction, grade and thickness above fluids, and all the data that we had entered initially in the this deck design is now visible here. So after that we can check the steel design. So here we can see that now this beam is passed. So you must be wondering what exactly is happening here, because initially this beam was getting failed, but now after when we are saying that this beam is composite, now this beam is passed. What exactly is the reason? The reason is simple, because when we make this section composite, then we are not talking about the moment of inertia of only this steel section. We are now talking about the composite moment of inertia, or in structural engineering term it is called transformed moment of inertia. So I shall request you to read the AISC 360 code. So I am repeating the concept again, that is due to the concrete on the top, this steel design have some extra capacity, because the concrete on the top gives us a composite or transformed moment of inertia for this whole section here. So we can see that all these beams are now getting passed, and only the bending moment is considered is like this here. So we can switch on this bending moments here. So here we can see that these are simple WL scale by bending moments that are coming here. So now we can see that the beams are now these small beams are now passed. Here we can see that the beams are getting utilized correctly, that is they are utilizing up to the 91%. So that is a good thing. Here also we can see that the utilization is in the range of 66. Here utilization is in the range of 77 mm, 77%, that is 0.774. After that, if we see the design of the columns also, so in columns also we have sufficient margin and we have scope of optimization. But here we can see that the bracings are now getting failed here. So in bracings the ratio is coming out to be 1.05. So we can go to select by specifications and all failed beams. So here we can see that the bracings are getting failed here, And in the meanwhile, there are scope of optimization also in the columns and in these primary moment resisting frames here. So we do need to increase this CH 150 75 18 to CH 200 75 23 double channel front to front. We can increase the spacing it to be 50 mm. And in the meanwhile, for this W16 by 45, we can reduce the size of these columns also. So instead of W16 into 45, we can check W16 into 40 also. And for this built up section here, we can change the thickness of the flange on the top. So now there are 4 warnings. So basically what we need to do is that we do need to take CS 275-23 and select double channel back to back and select it in the spacing of 50 mm, and then again analyze the structure here. So structural designing is nothing, structural designing with software is nothing but like trying different permutation and combinations, trying different arrangements, so that you can have a like a design which is economical as well as a safe design. So now there are no warnings here, and if we check the arrangement here, so here we can see that it is only now pass, that is in the range of 0.687. so everything below 1 is safe. And here also we can see that the columns are still having sufficient margin, and here also the capacity is now good, that is the utilization ratio is 0.865. so that is a good design, that you are utilizing the member up to the 87%. But for this you can again decrease the size. Let us say instead of W16 into 40, we can use W16 into 31. Let us check that whether this design is safe or not. So now again there are 2 warnings, that is the columns are getting failed. So it is desirable that you increase the size to W16 into 40 itself. W16 into 40 is safe, as well as like the deflections shall also be controlled in that particular case. So now we can see that the capacity as well as utilization is now correct. So when we go to select by specification and to check that whether any beam has failed or not, so no beam has failed for steel aluminum design calculation. So now our design is correct as well as economical. But things does not stop here. Things start here. So now if we go to the post processing mode here, so here we can see that there is the things like node displacement and reactions here. Under the displacement option, when we go to the summary, you will find the maximum displacement that are occurring in the structure. So here we can see that the maximum displacement is 4.304 mm along x-axis. So that is a very less displacement. Along y vertical, the maximum displacement is minus 6.6 mm, so that is also very nominal, and along z it is 0.199. so these deflections are very less. And in the case of reactions, we can see the maximum reactions here also. So the maximum Fy is 43 ton, and we can go to results, select view value and remove all. So here we can see that this 432 kN reaction is coming here for the 1 times dead load plus live load plus thermal load, and the maximum tension load is coming here, that is here. So it is only 2 ton vertical load, and these are the horizontal reactions, that is along x it is only 2 ton, but along z because of this bracing here. So here we can see that for bracing the loading is quite high, that is 24.4 metric ton along both directions. So now we have finished analyzing also, designing also. We can see the STAT output file also. So here we can see that these are the seismic parameters that has been defined. This is basically the center of mass and master joint number, and the base shear, design base shear as per the IPC 2012 is coming out to be 106.74 kilonewton. So the base shear percentage is 4.9% here, and the load factor is 1. So for all the values that has been entered here, the total seismic weight is 215.82, which we multiplied it with 4.9%, comes out to be 106.74. that is a design base shear. And similar is the case for the along z direction also. So time period used is the calculated time period is 0.135 along the z and 0.335 along the x. So you also should know how to read this design output file. And when we see our design results here, so here we can see the tau b values, delta values, and all the forces, and tau b has converged for load case number 25. So similarly, all the design results have been given here. So these are the composite sections that have been designed. So I hope things are now clear to you, that how we can do the analysis and design. Similarly now, when we go to the report option here you will see the floor vibration report option. So that we will study in the next lecture. So in this lecture we shall learn how we can generate the floor vibration report. So floor vibration report I had already explained in the previous lecture, that for the steel composite deck structures, floor vibration and analysis is a very important analysis, and this analysis is done by the ETF software also. It is done by the, I think, SAP also, RISA also, and STAT also. So when we refer the STAT help manual, so there is a separate topic on the floor vibration analysis. So the adequacy of floor system from the standpoint of its vibration serviceability due to human activity, specifically walking excitation, like it may be a dance floor, or it may be a floor on which there may be some army training. So for that you may need to study, and basically the vibration calculation is done for the beam or joist mode or girder mode. So the output of combined mode consists of this peak acceleration of walking excitation and allowable acceleration. So allowable acceleration is given in the AISC for different types of uses. That is, for shopping malls it is different, for offices it is different, for footbridges it is a different number. So this is basically the theoretical basis, that is fundamental natural frequency. It is 0.18 G divided by delta square roots. And for the combined mode, that is delta G and delta J. The combined mode, the fundamental natural frequency can be calculated from this particular equation. And delta G is the joist deflection, and delta G is the girder deflection, and delta J is the joist deflection. and this is nothing but the equation that we studied in our college, that is delta is 5WL4 by 384 EI. So in this case the W is like a function here, and this is basically the equation. So this is this transformed slab moment of inertia that I was talking to you earlier also. That is why the IP 240 had failed when we had considered it as a steel beam, but it get passed when we had considered it as a part of a composite deck system. So the transformed moment of inertia is the thing that helps, and all these equations have been given here. That is how the stat calculates the frequency here. And there is also one tutorial problem here. So this is the way with this we had also modeled this composite deck system here, and this is the option with which we can calculate the floor vibration report. So coming back to our model, we need to go to floor vibration report. Here we need to select the decks. Let us say we need to go do the deck this floor vibration analysis for deck number 1. Load case, we need to enter the floor vibration. Building type, we can enter it as let us say this office residence, and check. So here we can see that now this is basically the beam mode or joist mode that we were talking in the help manual. This is the girder mode, delta G and delta J, and this is the combined mode. So the combined mode or the combined acceleration that is coming here is approximately 2.2124 against 0.5 here. So the things are not much correct here. So let us say whether this floor is safe for the outdoor foot overbridge. So here we can see that as in the outdoor foot overbridge, the acceleration is again high as compared to this, but in the case of this office here, again this value is quite high. So basically, as per the floor vibration report, we do need to strengthen our structure because it is not passing in this vibration analysis. So this is just a simple check that we can do for any structure. Like this particular arrangement cannot be used in any type of structures. So either we can increase the thickness of the RCC slab, or either we can increase the size of the beams so that this deflection may comes under, the vibration may comes under control. But otherwise the allowable acceleration is 0.5 and our acceleration is 2.2124, and it is almost 4 times here. So this type of things may help you to analyze or ascertain that whether the floor is safe in the vibrations or not. And we can also have the printout of this option. So these are just the secondary options here, but the most important things are this delta G and delta J, and how these values are combined to give you the final result here. So I hope things are now clear to you that how we can check the floor vibration. And there is this one more thing also, that most of the people ask that they want to create a design report of this. So either they can make a design report manually, or what we can do is that we can just take pictures here. And we can go to the post-processing mode. Here there's an option called reports. So in reports we can enter the steel design, all check results, all select results, and after that we can enter the load cases also, items also. Here we can also enter the pictures. That is, we have taken the 3 pictures here, so all the 3 pictures have been entered here. After that we can enter the outputs also, earthquake checks also, steel design output, or node displacement summary, steel design detail, utilization ratio table, name and logo. If there is a name and logo, you can also select it from your system here. So left click on OK here. So now you have got this design report here, and this report is approximately very long report here that we are getting here. So we can left click on print here. We can name it as PDF. So I hope at the end of this lecture you have learned how you can check the floor for the vibration analysis, and how you can take a printout of the design report with all the desirable design results that you want to submit to your client. So at the end of this lecture, I hope you have learned how you can analyze and design a structure as per the AISC standards allowable stress design. So now when we have studied everything about the composite steel construction as per the AISC ASD, there is this one concept that is still pending, that is how we can check for the deflection as per the STAD. So most of the people do ask me about how what exactly is the DJ1, DJ2 concept and DFF concept. So I shall explain you, I want to explain you in this lecture itself. So basically the thing is that the beam that we do need to consider is from this point to this point. Okay, number one concept. Number two concept is, when we are talking about the deflection of the beam, we are talking about the deflection of the beam from this point to this point, and the maximum deflection shall be around this particular area here. So as I had always also told you earlier also, that we do need to enter each and everything in STAD. So we do need to tell the STAD that this is a member from this point to this point, and the joint with which we are talking about is joint number 23 and joint number 24. So let us say we left click on define parameters here. So we enter the DJ1 here as 23 and DJ2 we do need to enter as 24, and there is this one DFF parameters. Let us say the allowable deflection as per our requirement is L by 250, that is 7250 divided by 250. 29 mm is the allowable deflection at the center of this. So we do need to enter 250 here. So now DJ123 needs to be assigned to this particular beam here, and all these beams needs to be copied to DJ224 here, and again we do need to assign DFF parameter also. So I hope things are now clear what exactly I am trying to convey here. That is, for all the beams that are from this point to this point, from this point to this point, we do need to enter DJ1 and DJ2. So this is a very hectic and tedious task, which may takes up to a full 1 man day of an engineer to do, and the software like ETABS and SAP do it without these type of things.